exponential growth and decay. So just to review a little bit, when we talk about an exponential model, it arises in situations where a quantity increases or decreases. And if you remember, we talk about an exponential function where your base is a constant and the variable is in the exponent. So we're going to take a look at the differential form of what an exponential equation and exponential growth looks like. So when you have a quantity y is equal to yit, it's said to have an exponential growth model if it is increasing at a rate that is proportional to the amount of quantity present. It could also be that we have an exponential decay model if it is decreasing at a rate that is proportional to the quantity present. So again, exponential growth versus exponential decay. Thus, for the exponential growth model, the equation will satisfy the differential form. So your dy dt is going to be equal to k times y, where k is your rate of growth, and again, your k value is positive when you're dealing with exponential growth. So you do have to know, ladies and gentlemen, what your exponential growth and decay derivative models look like. So your dy dt is equal to k times y, and if k is positive, you know it's exponential growth. If you're dealing with exponential decay, you're still going to have it in the form of k times y, but it's going to be a negative k value. K will be less than 0. And k is called the growth constant or decay constant, which is why if it's negative, we call it a decay. Or it's also referred to as the proportionality constant. So just to kind of talk about where here's your dy dt is equal to k times y, for example, because most of the models we're going to be looking at, it's going to be referring to the independent variable as time. So you're going to see in the form of dy dt instead of an x. So let's suppose you're given your differential form of dy dt. And let's suppose that we want to find out what the equation of our exponential growth and exponential decay models are going to look like. So we do have to use our separation of variables. Remember what we did last night for homework. So I'm going to multiply both sides by dt and divide by y. So I have dy over y is equal to k times dt. So I'm going to integrate both sides of the equation. So again, my left-hand side is going to be the natural log of the absolute value of y. Remember, k is just a constant, so I have kt plus c. So any questions on how I've integrated both sides? Now, how do I start solving for y? What am I going to have to do to both sides of this equation? I'm going to have to do what? Raise it to the, exponentiate the equation, raise it to a base of e. Because e raised to the natural log of y is just going to be y equals, again, I talked about this the other day. When you see addition in the exponent, you can undo your properties of exponents. Remember, you add exponents together when you multiply like bases. So I can rewrite this as e to the kt times e to the c. Well, e to the c is just a what? It's just a constant. So y is equal to c times e to the k times t. So there's your exponential growth and decay model. So there's your differential form of your exponential growth and decay. Here's your exponential growth and decay equations. Again, just a reminder, if you look at the graph of exponential growth, where your k value is greater than 0, we know this is growth. Graphically, remember you have that horizontal asymptote for your exponential functions at y equals 0. And it's increasing as your x values are getting larger and larger. Again, if you're dealing with your exponential decay model, Again, your K value is less than 0. This is your decay. Remember, you still have a horizontal asymptote at y equals 0. But as your x values are increasing, your y values are decreasing. It's decreasing over time. Okay? So any questions about the difference between the growth and the decay? All right, so this is where we'll need some calculators. So again, take a look at some examples. So you have a town of Grey Rock. It has a population of 10,000 in 2006 and a population of 12,000 in 2011. Again, assuming that you have an exponential growth model, so always write down what the model is going to look like. So it's going to be y is equal to c times e to the k times t power. In what year will the population reach 20,000? So what are they asking me to solve for here? Are we solving for y, or are we going to be solving for t? T, because again, they're asking about what year. So when you're dealing, if you remember from last year, when you're dealing with exponential growth and decay application problems, if that constant growth rate or decay rate is not given to you, you always have to start by finding k first. You can't answer the question until you actually find k first. So that's got to be your first step. So nowhere in this problem does it tell you what that k value is or what your rate of growth or rate of decay is going to be. So this is where you're going to have to use this information given. So they're giving me a value of the population in 2006. So in 2006, my population is 10,000. So I'm going to call that year 0. So at year 0, my population is 10,000. In 2011, they're telling me my population is 12,000. So the difference between year 2006 and 2011 is 5. So in year 5, my population is 12,000. So I'm going to use those two data points to help me calculate what the k value is going to be. First of all, looking at these values of the population, what are we going to expect the k value to be, positive or negative? Positive, because you see the population's going up. So what I'm going to do, I'm going to take in year 5, I had 12,000. Now C is your initial amount. So how you solve for C is if you take your initial value right here, that 0, 10,000, you can plug it in. 10,000 is equal to C times E raised to the k times 0 power. Even though we don't know k, we know that k times 0 is 0. So you can see that C will just turn out to be that initial amount. So for all of those, that's what that C value is going to be. So what I can do is I can take this equation and set it equal to 12,000. So 12,000 is going to be equal to 10,000 times E raised to the k times, and again, in year 5, that's when my population was equal to 12,000, so I'll plug in 5 for T. So any questions on how I set this up? Again, we've got to find that k value first before we can actually answer the question. What's going to be my first step to solve for k here? Divide by 10,000. So that's going to be 6 over 5 is equal to E raised to the 5k power. Then what? Natural log. So the natural log of 6/5 is equal to, again, when I take the natural log of E raised to the 5k, that's just going to give me 5k. And I'm going to divide by 5. So this is your k value. Is that my final answer? Does that answer the question? No. We're going to use that to actually calculate the answer. Now, when you get this k value, what you always want to do, you're not going to round this k value. You always want to store it in the calculator. Because what happens if I take this k value and I round it, then I use it to round another answer, the rounding can become significant and get you further and further away from what the actual answer is. So the way you store, in case you forgot, you're going to take the natural log of 6/5 Again, make sure you close your parentheses after you type in the 5, and we're going to divide it by 5. There's the store button, which is located right above on. Now, you have the whole alphabet that you could store this in the calculator. So if you actually wanted to store this value in for K, you could. You would have to hit alpha and that left-hand parenthesis. But I just always use an X. Just one less keystroke. So now anytime you hit an X on the home screen, it's going to plug all those decimals in for K for you. All right, so any questions on how you can store that value? Now you can go ahead and you can answer the question. So assuming an exponential growth model, in what year will the population be 20,000? So now that I know K, and we already talked about how we're going to solve for T, I'm going to take this equation and set it equal to 20,000. So 20,000 is equal to my initial amount of 10,000 times E raised to the K times T. And again, remember, K is what's stored in the calculator. So now I'm going to solve for T, so I'm going to start by dividing by 10,000. So when I divide by 10,000, that's going to give me 2, is equal to E raised to the K times T. Remember, K is what's stored. I'm not solving for K, so now I'm going to take the natural log. So natural log of 2 is equal to KT. Divide by K, which remember I've stored in for X. So then T is going to be approximately equal to the natural log of 2 divided by X. So I end up with about 19.009. Is that an acceptable answer? No. Because what did I call year 0? I called year 0 what? 2006. So I have to take 2006 and add 19.009 to it. So it's going to be in what year? It's going to be in the year what? 2025. Okay. So any questions on that? Remember, if that K value is not given, you always have to find that first before you can actually answer the question. All right. Another application of your growth and decay is the half-life problem. The half-life problem is when we're talking about, and it doesn't necessarily have to be half-life. They could give you another time period as well. But this is the time it takes for half of your element to decay. So again, obviously, we're talking about decay, so what does that tell you about the K value? The K value is going to be negative. So we have polonium-210. It's a radioactive element with a half-life of 140 days. Assuming that 10 milligrams are placed in a lead container and that Y of T is the number of milligrams present T days later, they want us to find the formula for Y of T. So again, because we're dealing with exponential decay, I need to write the model Y is equal to C times E raised to the K times T. Well, first of all, what is the initial amount of polonium that is given to me? The initial amount of polonium is what? 10 milligrams. So I know my C value is going to be 10. So now, the only other thing I have to do is I now, just like all the other problems, in order to write this model, I have to find K. So now they're telling me that the half-life is 140 days. So in 140 days, how much polonium is going to be left if my initial amount is 10? 5. So I'll have 5 milligrams present. So now I can use that 140 days and 5 milligrams to help me solve for K. So then I know that 5 is going to be equal to my initial amount of 10 times E raised to the K times 140. So I can divide by 10. I have 1/2 is equal to E raised to the 140K. Then what can I do to both sides of this equation? I can take the what? Natural log is equal to 140K, and then I can divide by 140. So K is equal to the natural log, and again, you could write 0.5 or 1/2 over 140. So now I have the pieces to actually write the equation for part A. So Y is going to be equal to 10 times e raised to the natural log of 0.5 over 140 times t. Okay. So any questions on part A, coming up with the equation? Yeah, Esther? If you type in the natural log of 0.5, because that's a fraction, it's actually going to be, it will be negative.
Okay.
Because if you remember your division rule of exponents, because this is a quotient inside, it's actually the natural log of 1 minus the natural log of 2. And natural log of 1 is 0, so it is a negative value. Good question. So now let's go ahead and answer part B. How many milligrams will be present after 10 weeks? So I want to find my y of 10. So all I'm going to do is plug 10 into this equation that I wrote for t. So y of 10 is going to be equal to 10 times e raised to the natural log of 0.5 over 140 times, now be careful of your units. 10 weeks, remember, 140 is not, this was not in weeks, this was in what? Days. So I need to convert 10 weeks is equivalent to 70 days. So make sure your units are consistent. So I need to plug 70 in for t. And again, I would still store this k value in my, it's a lot easier to type an x in than it is this particular fraction in for x. So again, I'm going to go ahead and store that on my calculator. So the natural log of 0.5 divided by 140, hit my store x. And there you can see that's where the negative sign is going to be when I store that k value. So 10 times second ln, and it's going to be 70x. So I have about 7.071 milligrams of the polonium after 10 weeks or 70 days. So any questions where I got the 7.071 milligrams? Part C. How long will it take for 70% of the original sample to decay? So I'm solving for t. Does everybody agree with that? So I want 70% of my original. How long will it take? So how much is remaining? So I want to know at what time how much of this polonium is going to be left. So what am I going to set this equation equal to? I'm going to set it equal to what? I'm going to set it equal to 0.3 times my original amount, correct? Which is 10. Because I want to know when I have 30% of 10 milligrams left. Equals 10 times e raised to the k times t. And again, remember, k is stored in my calculator. I always, instead of having to write that awful fraction over and over again, I just take k and I circle because that reminds me that that's what's stored in my calculator. So any questions on how I've set up this equation? So obviously I can divide both sides by 10, so that's going to give me 0.3 is equal to e raised to the k times t power. So I'm going to take the natural log of both sides, so the natural log of 0.3 is equal to k times t. And then I can divide by that k value I've stored in the calculator. So natural log of 0.3 divided by x. So it's going to take approximately 243 days, 243.175 days. Okay. So any questions on that particular example there? So here they're telling me it's similar to your half-life, but we're talking about bacteria. But they're saying the amount of bacteria doubles in 3 hours. And how many hours will the number of bacteria triple? So again, I'm still going to set up my equation y is equal to c times e raised to the kt power. So sometimes they won't give you that initial amount. But you don't need it to actually find your k value. Again, you still have to start all these problems the same way. If it's not given, you have to find that k value. So what do I know about my initial amount? I know that the amount of bacteria is going to double in 3 hours. So when t is equal to 3, I will have twice as much as the initial amount. So I could take 2c, set it equal to c, times e raised to the k times 3 power. So even if they don't necessarily give me a number for that initial amount, as long as they tell me a certain time period where I'll have double or triple the amount. So I'm going to divide both sides by 2, so 2 is equal to e to the 3k, natural log, and divide by 3. So k is equal to the natural log of 2 divided by 3. Looking at your answer choices, what kind of question would this be? Calculator or no calculator? No calculator. So some of these questions will be no calculator. So there's no sense even really dumping this in the calculator. We're going to want to leave it as the natural log of 2 divided by 3 in our calculation. So now we want to know in how many hours, so I know I'm solving for t, will the number of bacteria triple? So I want to find my y of t when I have got 3c of the original amount. So I'm going to take 3c, set it equal to c, times e raised that natural log of 2 over 3 times t. Divide both sides by c, so 3 is equal to e, raised the natural log of 2 over 3 times t. Take the natural log of both sides, and that'll leave me with a natural log of 2 over 3 times t. Now how do you solve that? How do you solve for t here? Multiply by the reciprocal, exactly. So I'm going to multiply both sides of this equation by the reciprocal of 3 over natural log of 2. So 3 times the natural log of 3 will be in my numerator, divided by the natural log of 2. So my answer choice is going to be what? A. Okay. So like I said, sometimes these problems will be calculator, sometimes they'll be no calculator. So that's an example of when it will be a no calculator question. Okay. Last problem, which is a F bar Q. So notice they also are telling you that is a no calculator. So again, you have a population of wolves, and t is greater than or equal to 0. The population is increasing at a rate directly proportional to 800 minus p of t, where the constant of proportionality is k. So again, we're increasing at a rate. So I know that this is going to be an exponential growth or decay model where this came from. So if p of 0 is equal to 500, they want me to find p of t. Again, what are they giving me with this 800 minus p of t? This is not my function, this is my what? Because it says it's increasing at a rate. So this is the what? Derivative. So they're giving you the derivative. And if you remember, when we've got exponential growth and decay, remember what the model's going to look like for exponential growth and decay derivatives. Sometimes it may not be explicitly given to you like the k times y, but you want to make sure you put it in that particular form if it's not presented to you that way. So I know in exponential growth and decay, I'm looking at a model of dy dt is equal to k times y. So again, this is my y value. So I'm going to take dy dt and set it equal to k times 800 minus p of t. Because remember, they want me to find p of t. So remember, p of t is what I'm trying to find, which is my c times e raised to the k times t power. But all I know is the derivative. So what we're going to have to do is we're going to, actually should actually be a p, dp dt, because they gave it in terms of p instead of y. So I have to use my separation of variables. So I'm going to multiply both sides by dt. So dp is going to be equal to k times 800 minus p of t times dt. then what do you think we're going to have to do? Remember, k is just a constant. We're going to have to divide by that 800 minus p of t. So dp over 800 minus p of t is equal to k times dt. Then what? Then what do you think I'm going to do? Integrate. Well, I know the right hand is just going to be kt plus c. What about this? Is it just going to be the natural log of 800 minus pt? Don't forget your u subs. What would u be equal to? U would be equal to what? 800 minus p of t. What would my du then be? My du would be a what? Negative p of t. Or negative 1 dt. So remember, you're going to need a negative sign out here. So it's going to be the negative natural log of the absolute value of 800 minus p of t is equal to kt plus c. I made a cursive t. It looks like a plus sign there. Before I exponentiate this equation, yes, Sean? Yes. Oh, d. It's going to be dt. Before you exponentiate, isolate the log. So what are we going to divide both sides by? We're going to divide both sides by what? Negative 1. So natural log of 800 minus p of t is equal to negative kt. Do I have to write a minus c? No, because a minus c is still a constant, correct? A plus c is still a constant, so I can just leave that as a plus c. Remember, c is just a number. Now I'm going to exponentiate. Take e and raise it to the power. So I have 800 minus p of t is equal to c times e to the negative kt. So now I'm trying to solve for p of t, remember. So p of t is going to be equal to 800 minus c times e to the negative kt. Now they gave me that initial condition. The initial condition, they said that p of 0 is equal to 500. So now I want to find c. So 500 will be equal to 800 minus c times e. Again, since x is 0 or t is 0, this is all going to be e to the 0. So e to the 0 I know is 1. So if I subtract 800, that's going to give me negative 300 is equal to negative c. So c is equal to 300. So finally now, I can write my p of t is equal to 800 minus 300 times e raised to the negative k times t power. So any questions on part A? You guys go ahead. Now that we have this function, you guys go ahead and do part B for me. So part B, now that I have my function p of t, 800 minus 300 times e to the negative kt, go ahead and find your k value for me using that p of 2 equals 700.